Good morning, boys and girls. So I'm right here under Motion Week 5. Monday, you had a lecture. Well, you got the slides for PowerPoint Motion. I'm going to be right there. I'm going to lecture on the last topic, acceleration, starting now. So first, we have the definitions. I'm going to go ahead and push present here. Acceleration is simply speeding up. Okay, you may have all heard, an automobile, a car, the Ferrari, 0 to 60 miles an hour in 3 seconds flat. Now that 60 miles per hour is a speed, right, at that time. So let's say the speed gun or stopwatch is in the hand, and if that's instant speed, right? You stop that stopwatch. At that moment, it's going 60 miles an hour. But what about at 2 seconds? How fast was it going? It hadn't got there yet, right? It was maybe at 45. And then, of course, at 1 second, maybe it was at 30. And then at 0 seconds, it was standing still. So at any moment during that time, it was going at a different speed. So if you can see my hand across the camera, this would be a constant speed, right? That'd be constant. But this one goes slower and gets faster, faster, faster. Okay, so that's acceleration. It's the speeding up. So the unit is going to be a little bit different. Acceleration is the rate at which the velocity changes. So we got to ask ourselves, what was velocity again? It is speed, same thing as speed, but it's speed in a single direction. Therefore, it entails a straight line speed. Okay, so anytime you change direction, you're changing velocity. So you can change velocity in two ways. You can change velocity by going in a different direction, or you can change velocity by going a different speed. But as long as you're at a constant speed, more or less, in a single direction, you have velocity. So acceleration is a change and the rate at which that change occurs. Things change at different. Think about rust. Rust takes a long time to occur on some kinds of metal, and it can happen seemingly almost overnight on other types, things hanging out in the yard. I'm thinking about, at least in my junkyard. So, the rate, how fast it rusts, that's an acceleration process. So acceleration can be an increase in speed, and we saw this on the exit ticket, or you will if you haven't, but it can go from 0 to 60. Now, what about these drag car races, where they're going super fast, and then as they come to a stop, the parachutes pop open and they stop. Cars have analog brake systems. There's technology and engineering in the cars that we drive for how fast they can stop. And you don't want to skid, so they have this anti-lock braking system that allows them to kind of rotate slowly. All right, what I'm saying is it can be a decrease in speed as well. It's not only increasing. So I already talked about change in direction. So anytime you change the direction, you change acceleration. You decrease the speed, you're slowing down. That's also acceleration, but we call it negative acceleration. So you can expect negative numbers. Another word for negative acceleration is deceleration. So we could refer to it as decelerating, meaning slow down, but technically we can call it a negative acceleration. And then an increase in speed is the most obvious one that we're familiar with. So increasing speed, as we said, the example, car speeds up at a green light. As you get going from standstill, revving up until you get to the next light, you're slowly picking up your speed all the way. You hit 40 miles per hour in traffic, and then the next light turns red, and you got to slow back down. So in traffic, you're always accelerating, right? You're always speeding up or slowing down in between lights and in traffic and such. So it's almost constant acceleration. Again, it can be faster, slower. So the definition is how fast do you get fast? Decreasing speed example, car slows down at a stoplight. Changing direction, Example, car takes a turn. It can be at a constant speed, but even if it's at a constant speed, it's going in a different direction. So that changes the acceleration as well. My pictures. So how do we calculate it? This is what we're getting down to. So calculating acceleration, if an object is moving in a straight line, right? So all these assume what we call linear motion. It's a line, it's a straight line. We call it linear. Say that word. Good. Acceleration. It's your final speed minus the initial speed, okay? Final speed minus initial speed, divided by the time it took to make that change, okay? So the units of acceleration are in meters per second squared. So look at the ms2. It's just like speed, correct? Sorry, I got my pen. It's just like speed, except that we have this s2 here. So I'm going to do a quick or an easy example, if my computer lets me here. There we go. So let's say that car was going 0 miles per hour. It's sitting still. But it went from point A to point B, right? 60 miles per hour. That's mph. Don't mind my handwriting. And it did this in 3.7 seconds, right? So I had my stopwatch and I said, go. And I'm in the car, I'm watching. Stop. Got the 60 seconds in 3.7 seconds. So the formula, I took final speed was 60 miles per hour, minus, right here, minus the initial speed. What was the initial speed? 0 miles per hour. It's an H. And we divide all that by time. And the time was what? 3.7 seconds. Okay. So there we are. What's 60 minus 0? In this case, it's pretty easy. It's going to be a 60. And then 3.7. So really it's going to be a 60 divided by 3.7. So be patient. Don't get mixed up. This should be a space right here. This should be a space right here. It's just like an underscore. So final speed minus initial speed divided by time. You write all this out, you're going to feel real smart. Now, 60 divided by 3.7, when you punch that into your calculator, now let's see if I can get on my calculator here. Okay, so here's my calculator. I'm gonna put in 60, because 60 minus 0 is 60. I'll push the divided sign by 3.7, and then push the equal sign, and it's 16, right? So again, 60 miles an hour divided by 3.7 equals 16. So, well, I did figure to tell you the change in time, but change in time is again 3.7 minus 0. So it's still 3.7. Okay. So here's the problem we were working out. I changed it just a little bit. Now, by the way, I didn't tell you, but acceleration is represented with an A. So acceleration equals, again, final speed minus initial speed divided by time equals 60 over 37. And we saw it on the calculator. We're going to go ahead and round it up to 16. 16.12 something. You can rewind and look, but 16. So how do we write that? 16 miles. Normally we say per hour, but it's going to be per, actually it wasn't per, the hours crossed out in miles. Is going to be miles per second and squared. So that little 2, okay, that's kind of important. A little 2 on top of the S. It's actually written like this, S2, okay? So it's going to be miles per second squared. And second squared because we have the time here and here. Okay, so 16 miles per second squared. That's it. So let's go through another. Oh, come on now. Clear that. We're going to get on to oh, dang it. This does not want to cooperate. It's getting all weird. Here's another example. Acceleration, again, write the formula, your knowns and unknowns. So 16 meters or miles per second minus 0. So here's a car at standstill. 0 seconds has passed. It's going 0 miles per hour. You start the stopwatch. Kick it into gear. 1001. Now it's going 4 meters per second. And look at 2 seconds. You can just see the distance is further than what it was here at 1 second. 1 more second passes by. Look at the distance between second number 2 and second number 3. So 0, 1001, 1002, 1003, 1004. So the cursor had to speed up, right? So 1001, 1002, 1003, 1004. I had to move that cursor faster. It was accelerating. I had to accelerate the arrow cursor because every second the car was at a further distance. So how do you figure that out? So 16 meters minus 0. 16 is how far we traveled, divided by how many seconds? 4 seconds. So 16 minus 0, 4 minus 0 is 4. So we went 4 meters per second squared. This is your acceleration. Notice the speed is always different, right? Here we're going 16 meters per second. And over here, 12 meters per second. Before that, 8 meters per second. And then 4 meters per second. So at 1 second, he had gone 4 meters. But at 2 seconds, he had gone 8 meters per second. So he's getting faster as time goes on. This is acceleration. If the concept is kind of odd, again, just look at the math, let the numbers tell you. It's a very familiar formula, very similar to all the other ones. So here's a question for you. Skydiver accelerates from 20 meters per second to 40 meters per second in just 2 seconds. So in 1001, 1002, 2 seconds of falling, he went from going 20 meters per second to 40 meters per second. So what was the average acceleration between the start of the jump and the end of the jump? Again, final speed minus initial speed divided by the overall time. Here you don't have a 0 starting point, so it's 2 seconds, it tells you. The final speed was 40, so you write in 40 meters per second, minus the initial speed, which was 20 meters per second at the start of the measuring. Divide by 2, so 40 minus 20 is 20. 20 divided by 2 is 10. 10 meters per second squared. That's his acceleration rate. So can you use you can use two types of graphs: speed versus time and distance versus time. They will look different depending on what you're measuring. So here is speed versus time. Now we notice between every point, follow the point 0 to 1, crosses 1 square, rise over 2 squares, run. Again, 2 squares run over 1 square, rise. 2 squares run over 1 square, rise. 2 squares run over 1 square, rise. We're going to run 2 squares over, and we're going to rise up 1 square. We're going to run 2 squares over and rise up 1 square. This sounds pretty repetitive. So this was probably going at a constant speed, and therefore there was a constant acceleration. So acceleration that is constant will always be a straight line. It could also be a straight line in this way. Okay. All right. And that'd be a flat line. So if it's speed or velocity, that's going to mean constant standstill. So the line is straight. And let's see if it's going to let me do. There's a glitch in the software right now, and it's just not letting me do what I want to do. Can't even stop share. This is such a waste of video time. My apologies. Ah, you want to see me? Okay. Jiminy Christmas. Still doing it. So let's look at the next example. So here is speed versus time graphs. Acceleration equals rise over run. And once again, you can see at the bottom, I don't think that, 4 meters divided by 2 seconds equals 2 meters per second squared, right? So if each of these, you have a speed at 4, and we're over here on the 4. I don't want to go back into the drawing. I wish I could annotate on here, but it keeps glitching out on me. I'll put up a professional video here as well. And 2 seconds. So 4 over 2, and you have your 2 meters per second squared. Rise over run. So speed is increasing with time equals accelerating. The line increases. There it was. So as I was going, pick any 2 points, and you can do it. It's going to be the same, even if you only went from one point to the next point. As I said, 2 divided by 1 is 2, and 4 divided by 2 is 2. 6 divided by 3 is 2. So it's always going to be the same. All right, distance. Distance versus time graphs. On distance versus time graphs, a curved line means the object is accelerating. So we just saw the straight line. That's a constant accelerating. I mean, constant accelerating, not getting any faster. Between 0 and 2 seconds, it's pretty constant. But look at 2 seconds to 3, and then 2 to 4. It's going up faster and faster. That's because his speed is increasing. His speed is increasing because he is accelerating. And so the line's going to go up quicker. If you look at distance on the left-hand side, you'll see that he's covering a greater distance in less amount of time. So let's just pick between 4 and 5. If you look between 4 and 5, we went from 15 meters to over 30. So that's 15 meters difference within 1 second. Let's look at 0 to 1. From 0 to 1, we hadn't even gone 5 meters yet. So the distance covered was a lot less in that 1 second than between the 1 second of 4 and 5, which was 15 meters. We were going 3 times as fast. So he definitely accelerated between 3 seconds and 5 seconds. So what you want to remember simply is that on a distance graph, you see that curved or curving upward line, that's acceleration. Okay, so on distance versus time graphs, a curved line means the object is accelerating. Curved line also means your speed is increasing. So remember that slope equals speed. All right, 2 questions for you. Actually, I'll end with those. Above is a graph showing the speed of a car over time. How is the speed of the car changing? Is it speeding up, slowing down, or staying the same? And we're talking about the speed of the car. Look at your rise over run. Look at the direction of the line. It's not like the other lines. This one actually starts at 12 meters per second. And now at 6 seconds, it's going 0. That's correct. It slowed down and came to a stop. So it is decelerating, but the speed was slowing down. Number 2, what is the car's acceleration? We can calculate that, but you would also see, of course, that it was consistently or constantly slowing down. So here's the rise over run. So pick any 2 points and this would work. So count the run. You have 1, 2, 3, 4, 5, 6 squares, which represents from 2 to 5. That's 3 seconds. From 2 to 5. That's 3 seconds. The rise, now again, because we can decelerate, doesn't have to go up. It just means the vertical number. And it actually goes down 1, 2, 3 squares. And those squares represent 2's. So 2, 4, 6. So that's going to be a -6 because it did not go up +6. It went down -6. So look down here at the bottom. Acceleration is rise over run. So the -6 meters per second is the rise over the run, which is 3 seconds. -6 divided by 3 is -2. Okay, 3 goes into 6 2 times. Because it was negative, it remains negative. So whenever you see that negative number, that means it's a deceleration. It was slowing down, not speeding up. So again, acceleration is a change in speed or a change in direction. And it can be speeding up or it can be slowing down. I'm going to go ahead and, well, there you go. Which line represents an object that is accelerating? Pause this, look at it. The only one that is accelerating would be this black line right here. Okay, green is staying pretty constant. That's a constant speed, constant acceleration. But that black one curves up. Remember that? Curved lines going up represent acceleration. Go ahead and pause this so you can read that slide. I want to shorten the video for all my errors here. So you read that. Above is a graph showing the speed of a car over time. What would a distance versus time graph for this look like? Okay, what's the car doing? Is it curving upward or curving downward? Well, it's covering less distance over here over seconds 4 through 6. We're going less distance in the same amount of time. That means we slowed down. Pop quiz over the whole thing. You ready? My dog saw a squirrel that was 40 meters away. It took 6 seconds for him to run the squirrel. What was my dog's speed? What is the formula? Okay, good. Speed equals distance over time. So 40 divided by 6 is your answer. That would be the speed. How can a car be accelerating if its speed is a constant 65 kilometers per hour? Well, what? That doesn't even make sense, does it? Let's read it again. How can a car be accelerating if its speed is constant? That means it's not getting any faster or any slower. 65 miles. Oh, yeah. It can be accelerating if it changes direction. So change, which we usually do with the triangle, change in direction. Tricky. All right. So I hope that helps. And sorry, this was such a terrible video. I can't even stop the video right now without doing this. So you're going to see my ugly face. Ready, go.